All right, here we are. Good morning, everyone. I believe this is the sixth reaction video. It looks like this time we're going to see something with electricity and magnetism. This time I did a search for physics homework solutions, and I spelled the word homework out this time. So this looks like from a few months ago. Let's get it on here.
Good day, my angels. So,
My
here are
angels.
some solutions to lesson 1.
I bet you that's just the mascot of the school.
Lesson 6. Question number 1.
Okay. Whoa. Let's go back just a tiny little bit. Just a tiny. Oops. Forward. Just want to see. All right. I guess I'll hit play.
Lesson 6. Lesson 6.
All right, let's take a look here. So, lesson 6, we've got some terminal voltage, some batteries, some circuits. Okay, so I see where they're roughly at in their semester here.
Question number 1. Find the terminal voltage of a 6 volt.
That was cool that he copied and pasted it.
0.6 internal resistance. I need to draw this. So,
I need to draw this.
here's my cell.
Awesome.
This is 6 volts. There's an internal resistance of 0.6 ohms, and it's connected to a 7.2 ohm load.
Aha.
Find the terminal voltage. Okay. Step 1, I'll label down here.
So it looks like he's given the answer in parentheses. I'm not sure, but that looks roughly right? I mean, we know that the terminal voltage is going to be less than the actual ideal cell voltage. So I would expect it to be less than 6. So I think that's what's going on here is the answer is in parentheses, which is pretty cool. Also, the fact that he copied and pasted was awesome. And then the drawing was great. It's interesting because this is how we always model a real world battery. And one of the things that I think about when I draw these things is, does it matter which side the resistor's on? Should you draw a little dotted box around it? Or should you just, think that it's, I remember when I first learned this, I thought, well, why don't they just pull that resistor out? Open the box and pull the resistor out. And so, it's a model, right? And so these models are, this works out. It kind of explains what's going on. But of course, all of the stuff that's going on inside, getting the charges to move inside the electrolyte is sort of the cause of this. And it happens that the physical model of it is as if it's acting like a resistor. So anyways, I always think that's interesting, but I am very curious about whether this was always there on the student sheet or not.
Step 2, find total current. Don't know it. You know what? I'm going to jump right to step 5, which is rewrite this.
So I love the fact that he indicated the direction of the current all the way around, not just once.
Our total, because those two resistors are in series, is going to be 7.8 ohms. I went 7.2 plus 0.6.
So I like how he explained that, how he did that addition there.
Is going to be V over R total.
That was really cool. So he said the variable names and he wrote the numbers. That was actually really cool. Sometimes people sort of do that intermediate step where they'll write V over R and then they'll plug things in. But again, the power of video, right? He said one thing and he wrote another thing. Very cool.
It's going to be 6 divided by 7.8.
So awesome. I'd forgotten that you could do that. This is so cool. So it's like he plugged the calculator down and he plugged it in. Now, I'm sure a ton of you do that, but I have never used this particular app, but it's so awesome, especially if it's the calculator that they have. Did we actually see which buttons he was pressing? Let me go back a little bit here.
Is 0.7.
Oh, yeah. You can see what buttons he's pushing with the yellow cursor.
Is 0.7692.
0.7692. Write it all. Yes. I hate significant figures.
So that means I have 0.7692 amps going through that 0.6 ohm resistor right
Yeah.
So this is 0.7692 amps. So
I love the significant figures. That's awesome.
The terminal voltage is going to be 6 volts minus I times the little r. It's going to be 6 volts minus 6.
So that time he kind of mixed up when he wrote the variables and when he wrote the numbers.
6 minus answer button times 0.6.
Answer button.
And I get 5.54. Answer key says 5.53, should be 5.54.
Ooh, interesting. Interesting difference there.
Another way I could have done that is I could have.
So already I'm super excited about what he's about to do when he said another way I could have done that. But I just want to pause here and talk about, the 5.53 versus the 5.54. He's pretty nonchalant about it. He's like, well, it looks like we're in the right shape. I do wonder, I'm thinking about my own kids, in middle school. They're doing so much of this online homework stuff, and if you don't get every single digit right, it says, "Oop, you got it wrong." And so, if this was one of those sort of submit your homework digitally through an online system, 5.54 would be wrong if the system is expecting 5.53. And I could just imagine students just being like, I don't know what I did wrong. And my guess is it kind of depends where you round off. Let's think about that. If we were to round this up, make this current a little bit bigger. If this current were just a tiny little bit bigger, this whole term would get bigger, which means this would get a tiny little bit smaller. So yeah, I'll bet you anything that you get 5.53 if you round this somewhere. And it'll just nudge that up to 5.5, or nudge this down to 5.53. So I think that my guess is students were turning this in on paper because it sure looks like he's expecting them to show their work. So on paper, you'd be just looking for this. How would you grade this? You just sort of, oh yeah, I see what they did. Good, they're good, and maybe just ignore this, or maybe look to see if the student comments about it at all. So very cool. Now he said there's another way to do it. Let's see how that worked.
Just figured out that voltage right there because it's the only external resistor. So I could have gone 0.7692 times 7.2, and I also get 5.54 volts because that's what.
Okay, so let's see here. Again, if he had rounded up, this answer would have gotten a little bit bigger. I don't know how you get 5.53. Well, I guess maybe that other way of rounding.
Left over to power the actual circuit. So you can find the terminal voltage by going EMF minus what you lose going through the battery, or just by calculating what's left over for the battery.
All right, very, very cool. So wonderful job, drawing the circuit, which, could have been drawn vertically or however you wanted to. Really sort of attacking it a couple of different ways, talking about variable names and plugging in numbers, and then that calculator. Sorry, I know so many of you do it, but it's like, hey, here's this calculator. So I'd love to hear comments from people. Number one, what happens if your students don't have the same calculator? Number two, do you think that we should draw a little dotted box around here to indicate that this whole thing is the battery? Number three, does it really matter whether you draw it attached to the small end or the large end? Number four, should you really talk about the source of internal resistance, or should we just plug away? I think that the fact that the answer was less, that 5.53 was less than 6 is kind of the big deal, right? And then, of course, if you were to change the load on it, it could be a really big deal. If you put a 0.6 ohm resistor over here, you'd only have half the voltage. So, these are really, really interesting problems. And of course, this type of homework problem is sort of a muscle builder, right? Like, hey, come on, let's just start churning through this stuff so we start to get some intuition. At what point do you start to engage the students with sort of a narrative question as well? And I'm sure it was later on in this homework assignment. Well, that's it for today, you guys. Remember, physics teachers are awesome.